Hi, this is the Art of Engineering Solar Kiosk Common Project, and my name is Anthony Pensiero.
I'm Emily Rang.
I'm Mandy Lin.
I'm Roxin Zhang.
I'm Shen Shi.
We want to build a solar kiosk because it has been observed by both students and faculty that the outdoor area in front of Cuban Hall is not being efficiently used, considering that it is a frequently passed location and sees a relatively high amount of sun every day. The idea was proposed to build some sort of solar-powered structure which would give students a comfortable place to relax and study, as well as forward Columbia's attempts to become a green campus. Students have also been asking for new places at which to spend their dining dollars on campus. Our proposal consists of 5 parts: architecture design using SketchUps, amenities inside, how we provide electricity using solar panels, cost budget, and a template of a website that hosts energy information. The structure we designed is an elevated dome. The dome would be 15 meters, roughly 50 feet, in diameter. The inside space would be about 4 meters, 13 feet high, and the top of the dome would be elevated about 1.5 meters, 5 feet from the inner ceiling. The dome would be primarily made by reinforced concrete and will be supported by 7 reinforced concrete columns, 6 along the circumference and 1 in the middle. The structure can then be enclosed by a glass facade, which not only gives a pleasing aesthetic appeal, but also lets in a maximum amount of natural light during the day.
The solar kiosk has 5 amenities. Inside the dome are 1, a food bar, which may accept dining dollars, 2, 6 tables at which students can enter and study, 3, a small indoor fountain, 4, indoor plants and sculptures for decor, and 5, a revolving door to minimize heat loss to the environment. It also has 2 vending machines, 9 outlets at the table to power devices, 3 computers for student use, 1 of which can host the solar server, 2 televisions, 12 LED lights suspended from the ceiling, and heating and air conditioning systems. The vending machine has a power rating of 250 watts. Its cost is $4,000 per unit, and we will have 2 units for a total of $8,000. It has a capacity of 40 different snack options and has high visibility, full function display with energy-saving LED lighting. The LED lighting has a power rating of 15 watts. The cost is $25 per unit, and it lasts over 35,000 hours. The AC unit has a power rating of 9,000 watts. The cost is $2,632. The heating unit, on the other hand, has a power rating of 3,000 watts at a cost of $800 per unit.
When summed up over the entire day, assuming a 12-hour day from normal business hours of 9 a.m. to 9 p.m., and assuming worst case scenario that all the devices are running it all the time, the kiosk would consume 56 kilowatt hours of energy. That's also assuming that the heating and the air conditioning units will never run at the same time. If the AC unit is running for half the year and the heating unit is running at half the year, then the average of the power consumption is 6,000 watts. The solar system features the First Solar 390 PV module, an AC/DC inverter, wiring to connect the system, and the use of the New York City electricity grid in lieu of batteries. Instead of using batteries to store energy, the entire system can be integrated into the New York City grid so that the structure uses power from the electric company when the solar panels are not producing enough energy, and energy can be pumped into the grid when the solar panels are producing a surplus. It will be shown later that the system will ultimately produce a net surplus of energy, meaning that the company would send the owner of the kiosk a check at the end of the month for the amount of energy that was pumped into the grid. If the top of the dome is modeled by an ellipsoid, the surface area for half of the ellipsoid, which is the top of the dome, is equal to about 195 square meters, or about 2,100 square feet. Each solar panel has an area of about 0.72 square meters. Okay, and produces an average output of 68 watts, but can produce an output of up to 90 watts if optimal conditions are met. Assuming average power consumption of 68 watts per panel, the entire roof would produce about 18.5 kilowatts of energy during full sunlight. This is a diagram of the solar panels we are using.
In order to calculate the daily energy production, shading must be taken into consideration for both in winter and summer months. So the shading can be determined by a rendering of the shading of the structures that's generated through the SketchUp model. The model accurately estimates the heights of surrounding buildings by assuming each floor in a surrounding building is 3 meters high, and the number of floors in the buildings are known. And here we have two shadings from June 21, which is the longest day in the year, and December 21, it's the shortest time in the year. And these timestamps mark the boundary of for when the structure stops and starts and stops receiving full sunlight between 8 and 9 o'clock, and between 3:30 and 5 p.m. The structure does receive partial sunlight. So the amount of total sunlight the structure received can be estimated as 6.5 hours of full sunlight and 2 hours of partial sunlight, which makes 7.5 hours of full sunlight during the day. So if the shortest day of the year is considered in the same way, it can be determined that on the shortest day of the year, the structure will receive about 3 hours of full sunlight. This means that every day of the year, the structure will receive between 7.5 to 3 hours of equivalent full sunlight for an average of 5.25 hours a day. On the average day, when the roof sees 5.25 hours of full sunlight, the structure will profit 41 kilowatts hour. Assuming that there are 100 cloudy days per year, then the relatively no energy was generated. This means we have 265 times 41 kilowatts hours, which equals to 10,865 kilowatts hours per year will be profited. If 1 kilowatt hour costs $0.2 in New York City, then the roof will afford a profit about $2,200 per year after it emits all of the structure's own energy demand.
The cost of PV system. If the average price of solar panels are 80 cents per watt, then one FS 390 panel has a max output of 90 watt and takes up 0.72 square meter. Over the 195 square meter roof, the total cost of the panels will be therefore just under $20,000. Therefore, the PV system, which avoids the use of batteries, will cost around $24,000 to install. If the panels generate $2,200 profit per year, they will pay for themselves in under 11 years. This table provides a full cost budget based on the pricing extracted from Amazon and Google. The space will cost very little to maintain and will reap two sources of income, from the indoor bar or vending machines and from the solar system. Including the solar system, the total cost will actually be around $240,000. The solar server will be a website hosted from a computer in the building that can give live data as to how much energy the solar panels are producing at any given time, as well as how much energy the building is using. The server will be an excellent way for people to begin to understand the power and usefulness of solar panels, as the site will keep running statistics of how much energy was produced and used, as well as how much of a profit was made since the structure was opened. The system as a whole, using the estimated cost of the structure and the PV system above, the entire system will cost around $240,000. The solar panels themselves will generate around $2,200 per year, but the bar, which could be the main source of revenue, could potentially generate the same as other on-campus bars such as Cafe East, Yuri's Cafe, etc. In the future, it may be possible to consider a different placement of the solar panels. Instead of placing the panels on top of the small dome structure in front of Pupin, where there's a lot of shading from surrounding buildings, it may be possible to place the same amount of panels or more on the roofs of the surrounding buildings. The end.